Hello, and welcome to another Digital Differential Equations lecture video for Salt Lake Community College. In this video, we are going to finish going through Chapter 8.1 and look at the inverse Laplace transform. Now, in our last video, we introduced how to find the Laplace transform of a function using your Laplace transform tools. The fact that the Laplace transform preserves scalar multiplication and vector addition, and that we have a table of known Laplace transformations. Now in this video, I'd like to do the inverse Laplace transform. Given a function in your S domain, rewrite it back into your T domain. So let's get started with that. And we're on page 9 of your guided lecture notes. The inverse Laplace transform. A function f of t whose Laplace transform is f of s is called the inverse Laplace of f of s. Or to put it another way, if I give you a function f of s, I want to apply the inverse Laplace transform to come back with our function f of t. Of course, f of t is going to be the function such that if I did the Laplace of f of t, we would get f of s back again. Now again, think about this the same as you do integral and antiderivatives. It's the same process. And let's look at a couple of simple ones to get started. Let's find the inverse Laplace transform of each function. Now the inverse Laplace transform of 1 over s. This is one of the Laplace transforms that we did together. The Laplace transform of 1 over s is just 1. Why? Well, it's because the Laplace of 1 is 1 over s. Similarly, the inverse Laplace of 1 over s squared. Well, this is just t because the Laplace of t is, and if you get stuck, look back at your table of Laplace transforms. Say, what is the Laplace of t? So recall, the Laplace of t, or any power function, is n factorial over s to the n plus 1, so whatever your exponent is. So ours had an s squared. So recognizing our form, that means that n had to be a 1. So that 1 plus 1 became s squared. And if n is a 1, then 1 factorial is also just 1. So by form recognition, we want to be able to match it with our original function that we started with. So the Laplace of t, the Laplace of 1 over s is just t because the Laplace of t is 1 over s squared. Okay, so how about the Laplace of s cubed? So since the exponent is a 3, it must have been that it was t squared as an exponent. However, I don't think this is right. Notice that if you just did the Laplace of t squared, the Laplace of t squared using our Laplace table would be 2 factorial over over s cubed. And again, 2 factorial is just 2 over s cubed. But this is not what we had. We did not have 2 over s cubed, we had 1 over s cubed, which means I got to do something to get rid of that factor of 2. So I'm going to say, well, what if you decided to multiply this by a half? That extra factor of a half will cancel out that 2. So now you'd notice that the Laplace of 1/2 t squared would be the same as 1/2 times the Laplace of t squared, because the Laplace transform preserves scalar multiplication. And then the Laplace of t squared we just showed is 2 over s cubed. Notice those 2's would cancel and would be back at our original function in the s domain. So sometimes you have to modify your guess by considering what coefficients might need to be there. So let's try this one. The inverse Laplace of 2 over s to the fourth. Now, if you'd like to, you could rewrite this because the Laplace transform is a linear transformation. You could write this as 2 times the inverse Laplace of 1 over s to the fourth. This step is not required, but it might make it a little easier. And now think about s to the fourth for a minute. Because the exponent is a 4, that the original function in your t domain was probably going to be something like t cubed. But this is not right though. But notice the Laplace of t cubed, this is technically going to be 3 factorial over t, not t, over s to the fourth. Remember, 3 factorial is 3 times 2 times 1, so 6 over s to the fourth. But that's not what we originally had here. We had, if you want to look at it as 2 over s to the fourth or 1 over s to the fourth, and I'm going to focus here on 1 over s to the fourth for a minute. I had 1 over s to the fourth, not 6 over s to the fourth. So I think what I really need to do here is add or account for that factor of 6. So I think what we really want would be 2 times 1/6. And then we would have t cubed. If we want to verify this is right, notice that this is going to be the same as 1/3 t cubed. So now note if we did the Laplace of 1/3 t cubed, this would be 1/3 times the Laplace of t cubed, and the Laplace of t cubed is going to be 3 factorial over s to the fourth. Of course, 3 factorial is 6, and 6 in that 1/3 simplify, and we get 2 over s to the fourth, which matches our original function in the s domain. So what I'm trying to get to in this problem is sometimes you're going to have to account for constants that appear because of your Laplace transform. Okay, let's try a couple of others. Find the inverse Laplace transform of 3 over s plus 2 over s plus 1. Now, the Laplace transform is a linear transformation, so it does preserve scalar multiplication. So I'm going to write this as the inverse Laplace. Let me do both the scalar multiplication and the vector addition at the same time. this would be the same thing as 3 times the inverse Laplace of 1 over s plus 2 times the inverse Laplace of 1 over s plus 1. Now, whether from memory or using your Laplace table, you want to know that the Laplace of 1 over s, now if you're not sure, look back at your table. The Laplace of 1 over s is just 1. So this would be 1 plus 2 times the inverse Laplace of 1 over s plus 1. So remember, s plus 1, this is one that we did as a group together. Now, s plus 1 looks like this one, but if you're going to have s plus 1, it really means that a had to be a negative 1. Because if a is negative 1, this is s plus 1. And if a is negative 1, you'd have e to the negative t as an exponent. So this would be 2 times e to the negative t. And of course, I'm going to rewrite this so I don't have parentheses and just write it as 3 plus 2e to the negative t. This is your inverse Laplace transform of the given function. And then notice the inverse Laplace transform takes a function in your s domain and brings you back to the t domain. Again, this is your inverse. Okay. Let's give the next two a try. And maybe you can pause your video for a minute as you give the next couple a try. I'll see you here after the next two. Okay, let's see how you did. So you don't have to rewrite all of these like I'm about to do, but it helps to maybe break them into pieces. Using the fact that the Laplace transform is a linear transformation, we can write this as 5 times the inverse Laplace of 1 over s plus 2 minus 2 times the inverse Laplace of 1 over s minus 3. Now notice that both of these have the same form, and you should look at them as exponential functions. So remember, in general, the Laplace of e to the at is 1 over s minus a. This is what we're trying to walk away from in this example. So here it says s plus 2. And if it's s plus 2, that means a had to be a negative 2. So I think we get 5 times e to the negative 2t minus 2. So now you have in this one an s minus 3 in your denominator. That means that a had to be positive 3. Here a was negative 2. So we'd have 2e to the 3t. And this is your inverse Laplace. Notice it lands you back in the t domain. Okay, find the inverse Laplace transform of 2 over s to the 4th. Now, because of the denominator in this one, s squared plus 4, you should be thinking trigonometric functions. Now there were two trigonometric functions though. There was a cosine and a sine. So if you look back at your Laplace table, that if you're dealing with a sine of a bt, it's s squared plus b squared in the bottom, and then b also appears in your numerator. If you're working with a cosine function, cosine of bt has an s squared plus b squared in the bottom, but now it has a factor of s in the numerator. So the difference between sine and cosine is whether or not you have b or s in your numerator. So for ours, we have a 2 in the numerator. So this is going to have to be the sine of just 2t. Sine of 2t. Okay, last one on this page. Find the inverse Laplace transform of this function in your S domain. Now there's different ways you can think about this. If you wanted to, you could think about the exponential shift function. This looks a lot like the Laplace transform of just s over s squared plus 9 that has a shift of the s plus 1. You can do it this way, or you can look at it as noticing that this, because it has an s in your numerator and not a number like the last one, this has to be your cosine function. And so if you're looking at your Laplace table, the two ways you can probably approach this is by looking at form 8, which has that s minus a, or you can look at it as form 6 that has a shift of 1. And notice that will make these agree. So what I want you to get to with this example is that this has to equal e to the negative t, that's your exponential shift, and then this part here is your cosine of 3t. This is your function in your t domain. Okay, I'd like to do two more examples with you, but I'd like to show you the two examples right away so you can see how they're similar and how they're different. The next example, one shows the Laplace transform of this fraction, and one is the Laplace transform of this fraction. Now both of them are complicated and neither of them look like the table of Laplace transforms I gave you. Now the difference between the two though, and this is what I think is important to notice, is notice that this first one here, the denominator is factorable. So I could write 1 over s squared plus 3s as 1 over s times s plus 3. I think what you should be recognizing here is that because your denominator is factorable as distinct linear factors, that you can use the method of partial fraction decomposition to rewrite this fraction. Whereas in our next example that I showed you, your denominator is not factorable. And so we would need a different method for this one. So I'll work on both of these, but notice that if your denominator is not factorable, you have to apply one technique. And if your denominator is factorable, and recognize that as having distinct linear factors, then we're going to use partial fraction decomposition. So remember, with partial fraction decomposition, you want to rewrite your fraction 1 over s times s plus 3 as a constant over your first factor, plus b, a constant, over your second factor. You'd like to multiply by your lowest common denominator to clear your fractions. So here, when you multiply by your lowest common denominator, you'll get 1 equals a times s plus 3 plus b times s. Now, if we let s equal 0, then it makes this factor disappear. And if s is equal to 0, the left-hand side is 1. And if s is equal to 0, the right-hand side ends up being just 3a, which tells us a has to be 1/3. Similarly, if we were to let s equal -3, then that would make this factor 0. If s is -3, the left-hand side is still 1. If s is -3, this factor is 0, and this factor becomes -3b, which tells us b has to equal -1/3. So what this allows us to do is rewrite our inverse Laplace transform. Instead of looking at the inverse Laplace transform of 1 over s squared plus 3s, we're now going to look at the inverse Laplace transform remember, a, that's the 1/3, so 1/3 over s minus 1/3 over s plus 3. And because your Laplace transform is a linear transformation that preserves vector addition and scalar multiplication, we can write this as 1/3 inverse Laplace transform of 1 over s minus 1/3 inverse Laplace transform of 1 over s plus 3. And each of these we should recognize now. The inverse Laplace transform of 1 over s is just 1. And the inverse Laplace transform of 1 over s plus 3 is e to the -3t, which I want to simplify and write it as just 1/3 minus 1/3 e to the -3t. This is your function in your t domain. It's the inverse Laplace transform of our given function. So in this example, I wanted you to walk away with remembering your partial fraction decomposition technique. Okay, I have one more example for you. Last one. Let's find the inverse Laplace transform of this fraction. So here, because the denominator is not factorable, we will use the method of completing the square to rewrite the denominator. If you haven't looked at the method of completing the square recently, then this would be a nice reminder. So remember, with completing the square, what you want to take is your quadratic, your s squared plus 4s plus 13, and you'd like to rewrite it as s squared plus 4s, and then move the 13 way off to the side for a moment. And you'd like to add and subtract just the perfect number here. Add this number and then subtract the same number, so that after you add and subtract this perfect number, it makes it so that the first three terms are a factorable perfect square trinomial. And you want to remember, the number that you add and subtract is always 1/2 of this b term squared. It's always half of this term squared. So take half of 4, which is 2, square it to get 4. So you'll add 4 and then subtract 4. Of course, it should make it now that this trinomial is factorable. And I think it factors as s plus 2 times s plus 2. And then the last two terms here will be plus 9. And so we can write this as s plus 2 squared plus 9. And this is your completing the square technique. Now what this allows us to do is to think about our inverse Laplace transform as s plus 1 over s plus 2 squared plus 9. Now if you're looking at your table of Laplace transforms, you'll notice a couple of things. This is probably going to be trigonometric because of the form of it. And I'm noticing the s plus 1 and the s plus 2. And I'm thinking, well, these look a lot like, let's scroll back. It looks a lot like this cosine function. Well, now, it's not the sine function because the sine function has a constant in top that's related to that b squared. But the cosine has an s minus a on top. But notice the s minus a in the parentheses and the s minus a in the top has to be the same. And if it were the same, that'd be that e to the negative at, that exponential shift factor. But they're not the same. So what I'd like to show you here is some manipulation techniques. And what I'm trying to get you to see is that I wish that this s plus 1 and this s plus 2 were the same thing. So here's my trick, my adjustment factor, adjustment technique. What if on the top we rewrote it as s plus 2? But I got to make it equal to the original top still, so what if I did s plus 2 minus 1? If you were to simplify that top, s plus 2 minus 1 is the same as your original. And now we'll write this over s plus 2 squared plus 9. So although it's a manipulation to come up with that minus 1 there, it is equal to the original top this way. And now I want to use the fact that the that the Laplace transform preserves vector addition, and I'd like to rewrite this as s plus 2 over s plus 2 squared plus 9 minus the inverse Laplace of 1 over s plus 2 squared plus 9. Now there's two different pieces to look at now. First, there's this inverse Laplace transform, which this looks exactly like our cosine function that we looked at just a moment ago. It's a cosine function that has an exponential shift. Remember, the Laplace of cosine of 3t is s over s squared plus 9, which is very similar to ours, but we have that s plus 2, which tells me this is really going to look like e to the negative 2t cosine of 3t. Now, our second term. This looks a lot like the Laplace of a sine function. Recall now that the Laplace of your sine function is actually going to be 3 over s squared plus 9. And technically we have that exponential shift factor there again, the s plus 2. This s plus 2 creates our exponential shift. So maybe we can write this as, I'll get to that in a second. But the problem I'm noticing is that for a sine function, we need to have a 3 in top, and we have a 1 in top. So a little bit more manipulation. What if we decided to multiply by 1/3 and 3? Then technically the 1/3 and the 3 would cancel. They'd be equal. But now we have that factor of 3 that we need in top. So I think this will give us minus 1/3 e to the negative 2t, and now it's a sine of 3t. And this is our inverse Laplace transform. Now, this algebraic manipulation I'm doing is going to be essential when you look at your homework tonight, so I hope this gives you some familiarity with how to do those manipulations. This should also give you everything that you need for your Chapter 8.1 homework, so I'm going to stop there. I hope this video is helpful, and I'll see you in our next video.